Let's talk about, we're just gonna call it rule number two, or characteristic pattern number two, that you will notice when you write reaction mechanisms, right? Um, this one is about the loss of a leaving group. Now, a leaving group is exactly what it says. It's a group that leaves, right? But the groups that are allowed to leave or have the capability to leave, when they leave, they must be stable and they must be able to stand alone when they leave. I mean, if you want to be grown enough to leave, you got to be able to stand alone, okay? That's what your leaving group is. So, let us talk about some leaving groups that are common that you will run into when you write reaction mechanism. Your halogen, they're common, right? Your chlorine, bromine, iodine. The reason for this is because when your halogens leave and you have, for example, the bromide anion or the chloride anion, these are stable. They're stable. And they're stable because if you remember, your halogens are very electronegative. So remember, electronegative elements like to hug electrons towards themselves and hold on to the electrons. So of course, bromine and chlorine is happy to accept some extra electrons, hold on to them for themselves because they're very electronegative atoms. So these are stable. Your halogens, their anions are stable and they can sit alone. Water is also an excellent leaving group. Of course, water is a molecule, right? And it's a molecule and it's stable. So water can sit by itself, okay? So these are some of the popular leaving groups that you will run into in organic chemistry. Let us look at how the leaving group leaves. Now, a leaving group can leave without anything incoming to push it out. Okay, there are reaction mechanisms like that where the leaving group, I guess it got sick and tired and it just got up and leave, right? There's nothing forcing it out. So there are reactions where nothing forces the leaving group out. It can just get up and leave. So let's look at an example and let me show you how a leaving group will leave. So if a leaving group is leaving, this is how the arrow looks that indicate that. You go from, so here we have a bond between carbon. So, or there's a carbon here with CH3, 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 and a Br. Okay. Now, the bond between the blue carbon and your Br is where your arrow goes from. So the arrow goes from that bond onto the Br. If you have watched the video with the nucleophilic attack, you will remember, and I hope you do, that when you draw an arrow from a bond, right, that shows electron being shared between two atoms, this arrow means the two electrons that make up this bond now goes on to bromine. It's like bromine is stealing the two electrons now to be with bromine only. It's no longer being shared between the blue carbon and bromine. Okay, bromine is stealing the two electrons. Now, when how bromine steals it, clearly, if I'm stealing, I'm taking it, it's gonna break away with the two electrons. It's not sharing it anymore, it breaks away with it. So this is what this arrow indicates when you draw your product over here, right? Let us I'm just going to duplicate this and erase some things. So this portion of the molecule that I have left here, right, is the portion that you didn't do anything to. No action happened here. Blue carbon is still intact with these three bonds. Draw that back, okay? But your bromine, what your bromine has done is it left. It's your leaving group. Bromine got up and left, right? So bromine, we have these lone pairs here, three lone pairs. Put them back because I didn't use them for anything, right? But this little arrow here tells me that the two electrons in this bond, the bond between blue carbon and bromine, is now on bromine. So now I have to give bromine those two electrons. Bromine now has 2, 4, 6, 8 electrons, right? Remember, bromine has no charge when it has three lone pairs and one bond. The electrons here are no, the electrons here went on to bromine. So I gave bromine 2 electrons. These two red electrons are no longer being shared, so bromine will have a minus charge, okay? The bromine took the electrons and left. Bromine became more negative because the 2 electrons are on it now, not being shared. That's why I have a minus charge. Now let's go back to this, okay? Over here, my blue carbon has 1, 2, 3, 4 bonds, so it's neutral. It has no charge. But here it has 1, 2, 3, so it's lacking a full octet. It's lacking 2 electrons. It doesn't have 4 bonds, which means, remember, it's lacking. If electrons are negative and I'm lacking some negativity, I'm clearly positive. So there's a positive charge here. This is a popular reaction when you start doing substitution reactions. Let's look at an example where um, water is the leaving group. Before I move to that, please remember when we draw an arrow, it originates from a bond, and then the head shows the formation of either a lone pair or a bond. And I told you, whenever you go from a bond onto an atom, the head of the arrow shows the formation of lone pairs. Let's look at water being a good leaving group. This is an example where water is a good leaving. This is popular, by the way, where if you have a water molecule in your reaction mechanism, it can leave by itself without anything influencing that leave. So you draw an arrow from the bond here. There's nowhere else you could have drawn an arrow from, because what this is telling me is that I am putting the 2 electrons that is being shared between oxygen and, I'm going to make this carbon blue. It's telling me that the bond, the arrow here is telling me that the 2 electrons that is being shared between blue carbon and oxygen is now being placed onto oxygen, right? And it also tells me that oxygen, right, that has these 2 hydrogens bonded to it. Remember, you have to put these things back because you didn't lose them. It's telling me that the 2 electrons that I'm putting here from here is going onto the oxygen and it's breaking this bond. Whenever you take shared electrons and put them onto an atom, you're breaking the bond. You're breaking away, you're stealing the 2 electrons for yourself. And you're breaking the bond. Clearly, you're breaking up. If I'm taking, I was sharing before, but now I'm taking everything for myself. Yes, I'm breaking up, right? Leave it. Okay? So this bond will break. Let us show that in terms of what it results in. So let's do this. And I'm doing this because I don't want to redraw the entire thing. So I'm just going to duplicate it. Let's erase this. So if you look, I always do this. Always draw back the portions of the molecule that you didn't do anything to. We didn't do anything to down here. So see, I put it back, right? Now, if you look at our arrow, remember I said the 2 electrons here went with the oxygen. So let me draw that portion. Then we come back and talk over here. So here's my oxygen. I'm going to put back my lone pair. I didn't use these. Please put them back. The 2 hydrogens are also still on the oxygen. I didn't lose them or they didn't just magically go somewhere. Yes? Put them back. Now let's pay attention here. My arrow indicates that I put 2 electrons on this oxygen. Let's put them there. There's my 2 new lone pairs that I gave it. Okay, this is water. This is water. Okay, and you should know there's no charge on the oxygen in water. Or you could reason it out, right? You could look here and be like, okay, my oxygen has a positive charge. But if I put 2 electrons on this oxygen with a positive charge, we like to say you kill the positive charge. Positive, here I come, giving you two things that are negative, it cancels the positive charge out or it kills it. Negative coming in where the positive is removes the positive charge, cancels it. Plus, you should know that this is water. The oxygen on water has no charge. And from that introductory playlist, you should know that an oxygen has no charge on it when it has two lone pairs and two single bonds. Anything else, there is a charge. So for example, look at this oxygen. It has three single bonds and a lone pair. Has to have a charge, and a charge here is positive. I explained this in that introductory part if you don't know why this is positive, or you could calculate it. Let's look at what's left over here. This blue carbon here, your blue carbon here has a hydrogen on it that is not shown because it's a line angle formula. So let me put it in. So now we lost the water and my carbon, my blue carbon only has one, two, three bonds. Carbon with only three bonds must have a positive charge. It lacks a full octet, so it has a positive charge. I put this here because I know a lot of your questions will give you arrows and ask you to show the product based on the movement of these arrows. Now, the only arrow here that shows the loss of a leaving group is this one. Everything else is resonance, right? But I wanted to talk to you step by step about what each one of these arrows mean because I know this generally is a popular question where you're asked to show what the arrows are indicating. So let's talk about that. We're gonna do it one by one. And by now you should be able to at least tell me um, what the first arrow indicates, right? So here you have a lone pair, right, moving into a bond. It means that these lone pairs will now be here. But guess what? In chemistry, we don't make smiley faces. So if you're moving from a lone pair into a bond, it's not making a smiley face, it creates a bond, not a smiley face. Now, remember, you can't overfill your octet. So if I'm putting a bond here onto extra bond onto the nitrogen, now this is resonance. You lose, this bond is now broken moving here. Something, you should write these things down. If you're now moving from a double bond, so you're moving from a double bond onto another bond, right? We don't make smiley faces, which means that when I go from here to here, the electrons in here does not become this. No, we don't do that. It becomes a bond, right? And then the same thing here. This one here, so let me number these carbons actually. 1, 2, 3, 4, 5, 6. So between carbon, all right. So here, this will move in between carbon 1 and 6. So it's no longer here, right? It redistributed itself. This is now, that's what this arrow means. It means that this is here, right? Between carbon 1 and 6. The bond that was between carbon 6 and 5 is now between carbon 4 and 5. So let's put it in. It's a redistribution. We didn't do anything over here with this, leave that alone. Then if you notice here, what's happening, you move the electron, two electrons in this bond that is being shared between this carbon and this chlorine onto the chlorine. Remember, that's a breakup. Whenever you move from a bond onto an atom, it means that the atom where the arrow ends is stealing the two electrons for itself, right? Notice that is different from this. The lone pair here is going towards a bond. Don't make a smiley face, it makes a bond. Here, it's going from the bond onto the atom. Every time you have going from the bond onto an atom, it means the atom here, where the arrow ends, is stealing the electron. So you end up with plus Cl. Put these electrons back because they weren't in action. Nothing happened to them. And then I place 2 more electrons on it, and that's how I get a minus charge. So sometimes you'll be given like a structure and ask, and it's based on, they'll show you move the arrow movement based on resonance, or it will be arrow trying to indicate the product. You should be able to reason and know now what each arrow means. Here, don't make a smiley face. If you're going from a bond to a bond, you make a bond. All you're doing is redistributing the bond. We don't make smiley face, so remember your bond is 2 electrons. So either it's gonna remain a bond or it's gonna look like a lone pair. That's the only 2 options you have.